Yeah, I feel very awkward. I think I just gotta get into it.
Yo, get into it. I have headphones in, so.
Say no more. I mean, it's fine. I just gotta get into it.
Mozilla. I'm getting into Mozilla.
Salutations, fellow computer touchers, part-time gardeners. This is LeetCode day number 2. I'm just gonna jump into it. So I'm not really gonna teach the problems. I'm just gonna. These are the cards that are due. So I have 2 cards. First unique character in a string, and I'll pause the timer. And power of 3. First unique is linear time, constant space, and power of 3 is log n with constant space. So I have 2 cards due, and then I'm just gonna go for some random weighted problems after, and that's gonna be that. So it's not really gonna be very teaching. It's just gonna kind of be like, this is just the daily grind. It is what it is. So first unique character in a string. So the goal for this problem is gonna be linear time with constant space. And then I'm gonna set up just some Vim key bindings to make it simple. So you have first unique car. I'll make this bigger. And we're getting a string, and we have to return a number. So given a string s, which is a string s, the parameter here, find the first non-repeating character in it. We can't know the first non-repeating character without looking through all the characters first. So the best we can already do is linear time. Then return its index. If it does not exist, return -1. So our example is LEETCODE. And the first non-repeating character is 0. So if we take a closer look at this, if we were to create a map of keys to value, our map worked right with the map has keys to key to value pairs. If we look at LeetCode and we were to create a map of letters to occurrences, we would have L, which is 1, E, which is 3, T1, C, 1, O, 1, D, 1. Right, and so the first non-repeating character would actually be L, because non-repeating means it only occurs once. So we know that we have to iterate through the entire string, right, create a map, and then we can iterate through the map again. Iterate through the string again, double checking our values with the map. So we're gonna have a string to a number, right, for our map, and we're gonna const car of s. And this is gonna be a shorthand to actually populate the map. So we'll say if the map has the character, then we're gonna get the occurrences for that character, otherwise we're gonna return 0. And we're gonna do the map.set car of value plus 1. So when the map has the occurrences already for the character, we're gonna get that value, add 1 to it. If it doesn't have it, we're gonna set it to 0, and then boom, we're gonna add 1 to it. So from here, we just have to iterate over the string while double checking the values from the map. So we can do const car of s again. The problem here being that we actually have to return the index if it does not exist. And we have to return the index for the first non-repeating character. So we're going to do something more like where we can get the character and the index. You actually can't do that with a string, so we can spread it into an array and then do dot entries. And then what we can do for this, we'll say, hey, if the map sub or map get character, right? Get the occurrences for the character and it equals 1, and we're just going to return the index for that, right? If we make it out here, it means we never found a character with the first non-repeating index, so in this case, like AAB. If we search for a character that has a unique number of occurrences, so 1 in this map, there's only 2 occurrences, right? And it's going to be A and B, and both have 2, right? And none of them equal 1, right? So we'd return -1. 1. So let me double check it here. We have const map string to number, iterate over the string. Then I get the occurrences, get 0, car value plus 1. Okay, we destructure the entries to car and IDX. After I get the character, occurrence of the character 1 return. So let's try and run that. That number is not a assignable type string. Line 10. Arguing of type number is not assignable to parameter of type string. Argument of type number, not assignable to parameter type string. I might have these mixed. It might be IDX. And car, because it's saying argument of type number is not assignable to parameter of type string. And if these are flipped, then car would be a number, but it should be a string. All right, so you get the index first and then the value when you do entries. Okay, looks good. So we're doing 2 iterations over s, right? That's going to be 2n for the runtime. We're going to drop the constant, so it's just going to be linear time, and then constant space, since none of the variables that we're using for this algorithm are going to scale with input to the function. Now we might be thinking the map, right, would scale with input to the function. But if we look at the problem constraints, s consists of only lowercase English letters. Since that's the case, that means that for any arbitrarily large string, map will at most take up 26 keys. And so for the string that goes up to 10 to the 5 characters, we'll only ever have 26 different characters, right? And mapping those to occurrences, so it'd be constant space as well. So power of 3. Goal for this problem is going to be log of n with constant space instead of the Vim bindings. So we have a function is power of 3. We have n, which is a number. So we have to return a Boolean. Okay, so given an integer n, which is passed into the function, return true if it is a power of 3. Otherwise, return false. So we know if a number is a power of 3 if there exists a number x such that 3 to the x equals n. So what we're really doing is we're searching. Our search space is actually going to be, well, it depends on if n can only be positive. N can also be negative. But actually, n can only be, it only can be positive because if you do negative, 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 3 to the negative 3. What is 3 to the negative 3? I don't know. An integer n is a power of 3. There exists an integer x such that 3n equals 3 to the x. So we're really searching for an x here that can give us the value of n when we do 3 to the x. So is n a power of 3? We return true because 3 to the 3 equals 27. 0 is not a power of 3 because 3 to the 0 is 1. N is a power of 3 because the integer x that would equal n is 3 squared. So you can actually frame this as a linear search over the space of 0 to n, right, inclusively, right? But then you can actually, since our search space 0 through n is distinct, actually doesn't matter if it's distinct, but because our search space is ordered already, we can actually layer a linear search on top of it. I mean a binary search on top of it. So we'll do that. Left will be equal to 0, and right is going to be equal to n, and we're going to say while left is less than or equal to y, yeah, okay. While left is less than or equal to right. And we're going to calculate our midpoint, which is going to be the pivot, and we're going to do left plus map floor of right minus left over 2, right? And then our pivot is actually going to be x. So if we do 3 to the pivot and it equals n, then we can return true. That means n is a power of 3, right? And so if I have another case, right, else if 3 to the pivot is greater than n, so if we take a midpoint in our array, right, let's just say we have 0 through 5 through 10. If we take a midpoint, and let's just say we're looking for n is 9, if we do 3 to the 5, which is going to be a ridiculous number, that's going to be greater than 9. So we actually don't have to check any of the spots in between here, because we already know 3 to the 5 is too big, and 3 to the 10 is also too big. So in that case, right, we actually set right equal to pivot minus 1, and then we duplicate the same case for, I used the wrong sign here, greater than n and pivot minus 1. Right, else if we take the midpoint and our number is smaller than n, then we know everything even smaller than n is also too small. So we want to make left equal to our pivot plus 1. Right, and we're skipping pivot in both cases because we're already processing the pivot, right, with these ifs. So we want to go past it, we want to go before it, right, in the case where right is decrementing to the center, which is our pivot, or the midpoint in the array, and left, which is going to be incrementing forward. And then our final check out here, right, we're going to have one more case. So let's just say they pass in n equals 0, right? So left, for example, for this example too, if left equals 0 and right equals n, then both these are going to equal to 0. So left would be equal to right here, so we're going to calculate our pivot. Well, 0 minus 0 is 0, over 2 is 0, floor is 0, plus 0 is 0. 3 to the 0 is 1, which does not equal 0, which is n. 3 to the 0 is 1, which does not equal 0. So you go 3 to the 0 is 1, which is greater than n, because n is 0. Then we do right equals pivot minus 1. Well, right was 0, so pivot minus 1 is going to be negative 1, right? And then we're going to go to the top, right? Now left is going to be 0 and right is going to be negative 1. This condition is not going to work because 0 is not less than negative 1. Then we're going to come out here, so we can't automatically assume that what comes out here is false or true. So what we would do is we would say, we're just going to check anyway. We're going to do if 3 to the left equals n. I think this should work. So makes sense. Our runtime is going to be log of n because on each iteration we're going to have our search space. Since we're having our search space, it's going to be log of n constant space, since none of the variables we're using here are going to scale with input into the function. So this next problem is remove duplicates from sorted array. So we have function remove duplicates. We have nums, which is an array of numbers, and we're returning a number. Okay, go over this problem. It's probably going to be linear time and constant space. So given an integer array nums, sorted in non-decreasing. If it's not decreasing, then it's increasing. Remove the duplicates. So you have duplicates in this array in place such that each unique element appears only once. The relative order of the element should be kept the same. So I think you can ignore this second part here, because if it's sorted in ascending order and you remove the duplicates, it would still be sorted in ascending order afterwards. Since it is possible to change the length of the array, it's impossible to change the length of the array in some languages. You must instead have the result be placed in the first part of the array nums. More formally, if there are k elements after removing the duplicates, So if we remove the duplicates, there are k elements remaining afterwards, which means k represents the number of unique elements. And the first k elements of num should hold the final result. It's not matter what you leave beyond the first k nums. Return k after placing the final result in the first k slots of nums. Okay, so we have the number we're returning is the number of distinct elements in the array. Now allocate an extra space for another array. You must do this by modifying the input array in place with constant memory. Skip the judge code because it's confusing. Examples say if 1, 1, 2, they want us to remove the duplicates and return the number of distinct elements. If 1, 1, 2, if you remove a duplicate. If 1, 2, and they don't care what we leave after k, k is index 2, so we're good. So in here 0, 0, 1, 1, 1, 2, 2, 3, 3, 4, deduplicate it, and we still get all distinct numbers. I don't care what we leave after the number of distinct elements. So the index actually represents the index of the first index of the index after the last distinct element. 0, 1, 2, 3, 4. So you can actually do this with the the naive solution in n log n would be to iterate over the array, right? So if we copy this array, okay, it didn't copy. You copy this array, right? Let's just say we copied this array and we iterate through, and on each iteration, we're gonna check the current element, so 0, and the next element. What we would do is, if we find that the current index we're on and the index plus 1, so I and I plus 1 are the same. If I equal I plus 1, right, for the nums there, then we're going to turn the first index into infinity. Then we're going to go to the next index. Are these the same? 0 and 1 are not the same, so we're good. Now we go to 1 to 1. Are 1 to 1 the same? Change this to infinity. Are 1 and 1 the same? Change this to infinity. Next index, 1 and 2 are not the same, but 2 and 2 are the same. Change it to infinity. 2 and 3 are not the same. 3 and 3 are the same. Change it to infinity, and 3 and 4 are not the same. Then you could just call nums.sort, right? And then sort it in ascending order and return that. Well, but they also want us to return the number of distinct elements. Well, once we sort this, all the infinities would be at the end. You'd get 0, 1, 2, 3, 4 with 5 infinities, right? Well, if we wanted to return number of distinct elements, we just create a new counter, I equals 0, iterate through the array while we can't find, until we find infinity. So is 0 infinity? No. Is 2 infinity? No. Is 3 infinity? No. Is 4 infinity? No. It's 5. Right, and so we find infinity, we're on index 5, we return I equals 5. But faster solution would be to use the two-pointer approach. And so this first pointer is going to represent the last unique index, right? And we're going to iterate through the array. Right, well, we're going to start at index 1, right? It just simplifies the algorithm. So if num sub last unique IDX, right, does not equal num sub I, well, what are we going to do? We want to increment last unique IDX plus equal 1, and then we're actually going to place nums sub last unique IDX equal to nums sub I. Well, what's the intuition behind this solution? Well, if we run it with the array we have earlier, then at the end we'd actually return last unique IDX plus 1. But if we run it for this array here, actually an even smaller array would be simpler. Oh boy. If you run it for a smaller array here, right? Last unique IDX, we're just gonna abbreviate to LUI equals 0. All right, we're just gonna run the algorithm in our head. So if num sub last unique IDX, which is index 0, and I, which is equal to 1, are not the same. So num sub last unique IDX and num sub I are not the same. Well, are I and I the same? Are these two numbers that are referencing the same? 1 and 1 are the same. So we don't run this code branch at all. We go to the next index, I equals 2. Right? Now we're going to say, hey, is num sub last unique IDX, which is 0, piped it into the array, it's number 1, is it the same as num sub I, which is now 2? Well, 1 and 2 are not the same. And so if we look closer, what happens next? LUI, stop the timer, LUI gets incremented to 1, and then we actually swap last unique num sub I, which is 2, index 2, into num sub last unique IDX. So 1 here becomes 2. And then you'll notice that LUI equals 1, but there's 2 distinct elements. So we have to add 1 always, because we'll be off by 1. So what's the intuition behind the problem? If we duplicate these numbers, intuition is that we're keeping track of the run of duplicates, right? So if we start at 0 and 1, assuming there's duplicates here or not duplicates, we'll be fine either way. So if we try to keep track of this duplicate run, right, as soon as their duplicate run ends, so as soon as last unique IDX is not the same as where we are in I, well, what do we want to do? Well, we don't want to replace 1 here. If we replaced 1, right, we'd lose the one we have here, and on the next iteration, because 1 and 2 are not the same, we'd lose 1 again. So what we can do actually is increment LUI once, right? So we can retain one of the duplicates, and then we'll replace the actual duplicate with the current number. And so this serves a dual purpose, because now, since this number is equal to 2, the only way this dupe run can end is if we run into a number that's different. So if we iterate all through here, I equals 3, right here, and then I equals 4, right? And then as soon as we get to 2, 3, 4, I equals 5, we have the same code again. We'll increment LUI by 1 just to retain this second 2 here, and then we're going to replace this 2 with a 3. Then we'll be done. You can return LUI plus 2 because we can see that there's 3 unique numbers here. And so the time complexity of this is actually going to be linear time, since it takes us 1 run through the array of numbers to actually find the solution to the problem. And it's going to be constant space, because for any arbitrarily large array, none of this code is really going to take up any more memory than it does now. We're just going to have one variable and the array. So boom. It's the last problem for today. So